Welcome back. So we had concluded the last lecture with temperature dependence of carrier density. If you recall, we also had discussed about charge neutrality. So the total positive and negative charge has to be same in a semiconductor. So now we shall go ahead and we shall wrap up these discussions with a few notes, on things like high doping and incomplete ionization, and then we'll move to things like mobility and drift diffusion, so that we can discuss about current transport. Once we discuss about current transport, we can discuss devices like PN junction that makes the LEDs or photodetectors, solar cells, BJTs and so on, things like MOSFET and different kinds of transistors, optical devices. Everything can be understood when we understand how electrons flow, and that is carrier transport, and primarily governed by drift and diffusion sort of a transport. Okay, and for that we need concepts like mobility and velocity. And before understanding mobility and velocity, we need the concepts of carrier concentration, how they change with temperature, conductivity and so on. So that's what we are doing it. And if you recall from the beginning of this course, we had actually covered the basics of band gap, carrier concentration and reciprocal space, and now we are building up to the carrier statistics, how carriers are distributed and how we calculate the carrier density, things like electron and hole density and so on. So now today we shall focus on high doping effects, okay, and incomplete ionization, and we shall thus conclude this initial sections of a few lectures on carrier density, carrier statistics, and density of states and so on, so that we can move to devices. Okay, so today we shall come to the whiteboard now, and we'll get started with high doping effects. Okay, so if you recall, in the last lecture we had last few lectures we have talked about n type and p type doping, and how do we dope them by adding impurities. We know that. Now this equation is very very familiar to you, exponential of EF minus EC by KT. So I told you that this Maxwell-Boltzmann equation is valid when your EF and EC, this gap, is at least more than 3 kT, right? At room temperature this is around 78 millielectron volt. So that means it is slightly moderate or lighter doping, and this equation is valid under such a circumstance, and you can use this formula to calculate the electron concentration. NC very well. I told you that if your doping keeps increasing, then your Fermi level keeps going up and up, right? N type doping. And if your p type doping increases, then your Fermi level keeps coming down and down. So if I dope it relatively higher, okay, if I dope it relatively higher such that your Fermi level comes very close to conduction band, so that this gap, this EC minus EF, this is very close. So this is less than 3 kT. For example, at room temperature 3 kT is around 78 millielectron volt. But if I dope it very high, so that your Fermi level comes sufficiently close to conduction band such that it is less than 78 millielectron volt, say if I say that EC minus EF, this gap, this gap is suppose only say 50 millielectron volt at room temperature, which is less than 3 kT, then this equation of Maxwell-Boltzmann equation cannot be applied. You know why? Because this Maxwell-Boltzmann equation came, if you remember, from this equation equal to n equal to nc, the Fermi half Dirac integral, remember, and this expression can be actually simplified to this particular expression, exponential, only when the doping is light, or when your EF minus EC, this gap, is actually more than 3 kT. So if it is if it is higher, less than 3 kT, the doping is very high. So if the doping, so I am talking about n type, same will apply for p type also, is doping is too high, right? If doping is too high, which means for say n type, what it means is that your EF your EC minus EF, this gap has become less than 3 kT, right? That is called high doping effect. And for p type, it means that your EF minus EV has become less than 3 kT, right? So in this case, your doping is very high. You cannot apply Maxwell-Boltzmann equation to calculate n and p. What you do is use that expression was there, n equal to nc, this. You try to sort of do an approximation of this for a high doping, because calculating this exact integral will need you a MATLAB or Mathematica kind of a software, and it's little also complicated. So can we do some simplification? So that is an approximation called Joyce-Dickson approximation. Joyce-Dickson approximation. And this Joyce-Dickson approximation will basically help us to calculate the carrier concentration when your doping is high. Suppose I am giving you a practical problem when your conduction band and your Fermi level are very close. I tell you that this distance is only 50 MeV. Okay, what do you do now? How do you find out n? I tell you that Nc is equal to say 10 to the power 19. How will you find out n now? So if you recall, EF minus EC by KT is given by ln, right, of n by Nc, if you recall that, right, is given by n by Nc. Okay, that is your Maxwell-Boltzmann equation actually. This, the expression that I had written in the previous slide, sorry, this equation I have written, this is the equation actually. I am writing it in a different way, same equation, I am writing in a different way. So this is the expression, right. For Joyce diction, you add just one more term. You know what that term is? You add one more term, and that term is plus, I will use the blue color, 1 by square root of 8 n by Nc. This is your Joyce diction approximation that you can apply when your doping is high, so that your EF minus EC is less than 3 kT. If you can use this approximation and you can calculate n. For example, you see that this is a transcendental equation. It's in the form of log x plus some constant type x, right. So it's a transcendental equation. Finding n directly, you will have to do some numerical and iterative process, but it still can give you a better idea. So for example, if I tell you that EF minus EC is equal to 50 MeV, then how will you solve this equation, right? So it's very easy to solve now. So I have told you that EC minus EF is 50 MeV, which means EF minus EC is minus 0.05, right. That is 50 MeV is 0.05, right. So Joyce diction approximation says that EF minus EC by KT equal to ln n by Nc plus 1 by square root of n by Nc. Okay. So I am assuming 100% ionization. So whatever n type doping I am giving is equal to n only, I am saying, right. There is no p type doping. So we can replace this n with nd also, not an issue. Now this quantity, this quantity I can write as minus 0.050, and KT at room temperature is given by 0.026. So this is roughly around minus 2, not exactly but close to minus 2. This is equal to log of n by Nc plus 1 by square root of n by Nc. So this Nc is supposed to be given in the question. So suppose it is 10 to the power 19, right, sorry. So it is given to be 10 to the power 19. So now there is only one unknown. This is equal to minus 2, right, close to minus 2. So there is only one unknown. So you can actually do a couple of iterations, or even put a numerical solver and find out what is n, right. So that is good. Same thing can be done for p type also. So this is a high doping effect. So when your doping is high, right, when your doping is high, you have to apply Joyce diction approximation to find out the carrier concentration. Okay. And another thing is, if you keep doping higher and higher, then your Fermi level keeps going up and up, no. So suppose this is your conduction band, this is your Fermi level, valence band. If you keep doping high and high, eventually the Fermi level can actually almost touch the conduction band, very high doping. In such case, we call it as almost the degenerate doping. Okay, it's a super high doping. I am talking about n type only, but same will apply for p type also. When the p type, the Fermi level will touch the valence band. So here you see the Fermi level will almost touch the conduction band. It can even go above the conduction band, it can even go above the conduction. The Fermi level can be above the conduction band also. If you dope it extremely high, the conduction band might actually come below the Fermi level if it is doped extremely very high. If it is doped very high, no, very high doping, what will happen? Couple of things will take place actually. One very important thing is that your band gap of the material will slightly shrink or reduce. Okay, when you dope very high, your band gap will slightly reduce. So for example, silicon band gap is 1.1 electron volt. If you dope it very high, suppose you dope it n type with say 10 to the power 20, this band gap will now become smaller slightly. It might, I don't know exactly how much I forgot the value, but it will become slightly smaller. It might become 1 electron volt, or it might even become 0.9 electron volt. Do you know why? Because with very high doping, with extremely high doping, you are putting too many of substituent atoms into the crystal, they distort the lattice, and your periodicity gets also distorted to some extent, the periodic potential that you have, and you actually have you have this periodic potential. If you remember, the atoms are all equally spaced apart, right? And when you dope, it's actually like 1 in a million. So out of 1 million silicon atoms, only one will be replaced by, say, phosphorus. So phosphorus. But if you dope very high, then there will be more phosphorus, for example. So what happens is that the periodicity is sort of distorted, okay, and also that affects the band gap. So you have things like band tails, which means the distribution actually extends below that band gap also. So for example, if you have too many dopant atoms, if you have too many dopant atoms, okay, if you have too many dopant atoms, then because you're distorting the periodic potential, or you are distorting the periodic arrangement of the atoms, your what should be this EC and EV actually becomes little bit, what it becomes is that it becomes little bit jagged, like it becomes slightly like this, EC EV. The band gap is always same at any point, which is reduced slightly, but it becomes little jagged or little because this is a perturbation in the periodic crystal that will manifest itself as a not completely smooth conduction valence band overposition. There will be a periodic there will be like a potential fluctuations, okay, there will be potential fluctuations that will result in a band diagram like this. We don't have to deal with it in day-to-day device analysis, but it's just important to know that your there's a the fluctuation in the band edge, and there's something called band tails. So your Fermi-Dirac distribution will extend little below the band also, okay, will extend below the band also, and so your band gap also will shrink, right? Your new band gap EG dash will be slightly smaller than actually the true band gap of the material, okay. So there's a lot of interactions between electron and donors or dopants, right? So when too many interactions are there, and all these interactions, dopant interaction, these all interactions increase. These all interactions increase in magnitude when your doping is very high, and all these interactions seek to lower the band gap. Okay, so this is one effect we should keep in mind. With very high doping, for example, your band gap will slightly shrink. That is one thing we should keep in mind. It has very important implications actually later on devices. And also we should keep in mind that with high doping, your Maxwell-Boltzmann equation cannot be applied. So you have to apply a Joyce-Dickson sort of approximation. There are band edge perturbations and so on. So these are the things that we should keep in mind when there are very high doping effects. I told you conduction band, Fermi level can actually go above the conduction band. It's very much possible. It's degenerate doping. It's extremely high doping, and such high doping material are typically not used in many devices, but there will be some devices where you have to dope very high. So it's important to know that, okay. And then another thing we would like to discuss before we would go to topics of mobility and carrier velocity and other things which are important for transport is called incomplete ionization. We should just be aware of this term. We don't have to do the exact numericals or mathematics of this, but we should be aware of what is incomplete ionization. I had told probably in a very brief thing in some of the last classes, maybe I told you that in general, if I only consider say n-type doping, there's no suppose p-type doping, okay. N-type doping, I told you that if I add 10 to the power say 16 donor atoms, say phosphorus and silicon, all of them are actually ionized, which means all of them are giving electrons, right? So I will get 10 to the power 16 electrons per centimeter cube, right, electrons per centimeter cube. And so I say that the free electron concentration is equal to the donor concentration, right. This is assuming 100% ionization, or 100% of these donors are actually ionized, and typically they are 100% ionized, because I told you this is conduction band, this is valence band, and if I draw there's an ionization energy level actually, donor energy level. So this is ED. The donor that you are putting, like phosphorus, for example, you are putting phosphorus in silicon as an n-type dopant. If you put phosphorus in silicon, then this phosphorus will introduce a donor energy level which is very close, actually very, very close, okay. This energy difference between ED, the donor energy level, and EC is kT or less than kT, less than kT, which means at room temperature it is sufficient energy is there, thermal vibration, to put all the electrons up in the conduction band. all the electrons are put in conduction band, and that's why if you put 100 of this, all 100 will give electrons. That's why 10 to the power 16 will give 10 to the power 16. Same thing with holes also for valence band. Now, if for some material the doping is such that the donor ionization energy level is not so close, then what will happen? Then not all of them will get ionized, right? So, for example, I take EC, sorry, suppose I take EV here, and then there is a donor ionization energy level ED, which is little far away, because the donor the impurity that you are adding is such that it introduces a donor level little far away. Suppose this is 3 kT, or maybe say 0.1 EV, which is almost equal to 4 kT, almost, right. 0.1 EV electron volt is little large, 4 times the thermal energy. So, all the donor atoms that are there may not be able to give electrons. Maybe some of them will give electrons, some of them will not give electrons. Maybe if you put 100 of these phosphorus atoms or donor atoms, maybe only 60 of them will give electrons, rest 40 will not give electrons. So, we say only 60% has ionized, 40% has not ionized, and the donor energy level is ED. The further away this ED is from conduction band, more and more it is possible that the ionization fraction has reduced. Okay. So, what is the fraction that has ionized? So, I told you typically, if you assume 100% ionization, then Nd is equal to N, which is equal to Nd plus, because all of them has ionized, all the atoms have ionized basically, right. But if it is incomplete ionization, then this is not true, right. The fraction that is ionized, Nd plus by Nd, typically it is 100% if it is fully ionized, 1, that is 1, but if it is incomplete ionized, then it will not be 1. It will be something like this. Okay, it will be something like this. Okay. So, the fraction of ionized donors will depend as 1 by 1. This is actually a Fermi-Dirac distribution only, 1 plus 2 into exponential of EF minus ED. See, EF, the Fermi level comes into picture, minus ED, the donor level here. The Fermi level will be somewhere here, no? So, Fermi level minus donor level divided by KT. Okay. And this factor 2 comes because of spin. There are 2 states, there is a spin. So, the factor 2 comes there. So, for example, if I know the Fermi level position and if I know the donor ionization energy level position, I know that what fraction of donors has ionized actually. For example, if the Fermi level and the donor level are at the same time, at the same level, EF is equal to ED. So, the Fermi level and donor level are at the same position, then this will become 0, it becomes 1. So, it will become 1 by 1 plus 2, 1 by 3. So, 33% of donors will be ionized if Fermi level is equal to donor ionization energy level, right. So, only that. So, similarly for holes, I mean this is an important thing actually, not everything has to ionize. Similarly for holes, Na minus by Na, this is the fraction of holes that are not fraction of holes, the fraction of acceptors that are ionized. Remember, when they ionize, they give away hole or take away electron, so that have become negatively charged. This is the fraction that is ionized, that is given by 1 by 1 plus 4 exponential of Ea minus Ef here. This is the acceptor ionization energy by KT. The reason 4 comes is because of heavy hole and light hole, and then there is a spin. So, 4. Okay. You remember that for say n-type doping, your electron, only if you have an electron n-type doping, then the total electron in negative concentration has to be equal to total positive concentration. This will always be true for an n-type dope material. Okay. Even if it is incompletely ionized, it is always true. This Nd plus need not be equal to Nd if it is not 100% ionized. So, N will always be equal to Nd plus, but whether all the Nd pluses come from Nd, some of them may not have come from Nd. If it is 100% ionized, this will hold true. If it is not 100% ionized, this will not hold true, say 60% ionized or maybe 50%, but this will always hold true. Same thing with holes. Okay, this will always be true, but this need not be true. Okay, this need not be true. So, that that we should keep in mind. So, now if you have I told you that if you have both electron and hole doping, then the total positive charge is this, total negative charge is this. This will always hold true, except that this and this need not be 100% ionized. Okay, they need not be 100% ionized. They can be incompletely ionized also. So, for example, you have seen the white LEDs that you can buy from the market. You can buy white LEDs now for 100 rupees or so. These white LEDs are actually in fact blue LEDs, and these blue LEDs, they have a phosphor coating. They have a phosphor coating to convert the blue light to white. Okay, and these blue LEDs are always made up of gallium nitride. It's a semiconductor. All the white LEDs that you see in your parking garage, on the streets, in the airports, in your houses, to stadiums, all the white LEDs are actually made of gallium nitride semiconductor. And actually a gallium nitride PN junction, will actually be the white LED. That is what is happening. There is a little bit more to it. I am not telling you right now, but that is what is happening. We will talk about PN junction later. Why am I telling you this? Because in gallium nitride, p-type doping, for p-type doping, you have to add magnesium. The moment you add magnesium to gallium nitride, you can dope it p-type. This magnesium is very less ionized. You know what? Only 1 to 5% is ionized as a p-type, which means if I add 10 to the power 17 magnesium atoms, only 10 to the power 15 holes I will get. It is so low, and that has implications in the gallium nitride PN junction, which has implications in the white LED. So, these are important things that we should keep in mind. So, incomplete ionization is not something very fancy that we have to study only for our course. It is very important for practical devices like white LEDs, right. So, we should keep that in mind. Okay. So, now we have finished up many things. See, going from the beginning, we have defined semiconductor bands, right. We have defined reciprocal space. In this course, I am just taking a stock here. Okay. We have defined reciprocal space and things like Brillouin zone, why they are important, right. I have told you how energy bands are formed, and energy band gap is formed, right. How energy band gap is formed. If you recall the periodic potential, the periodic arrangement of the atoms, the periodic potential, right. So, how energy band gap is formed, and I told you about things like effective mass of electrons, how the entire quantum mechanics is captured in the EK diagram, and effective mass comes from there. Electrons going from valence to conduction band leaves behind a holes. So, I introduced the concept of hole, absence of electrons. Okay. These are things we had studied initially. Then we came about density of states to tell us how electrons and holes will populate the number of states that are there. Also, which depends on Fermi distribution, Fermi-Dirac statistics. And from there, we went to how to calculate carrier N and P carrier concentration. So, those we have discussed, how to calculate carrier concentration, what is doping, right. We have done that. And what are the other things we have done in the course till now? We have done about how temperature dependence of carrier concentration, temperature dependence of carrier concentration N and P. I have talked about high doping effects, right, high doping effects, talked about incomplete ionization, which is very important, by the way, incomplete ionization. By the way, in high doping effects, we have discussed about band gap narrowing. Band gap can shrink. In high doping effect, there will be band tails. We have discussed about things and how you apply Joyce-Dickson approximation to calculate charge density and so on. These are things that we have studied. Now, what is the next point in the agenda? The next point in the agenda will be to introduce mobility, mobility of carriers. Okay, mobility of carriers, low field transport. okay, low field transport, and after that we will introduce high field transport, and velocity, okay, carrier velocity. So, low field transport, high field transport will come. Along with that, what will come is drift and diffusion of carriers will come, so that we can understand electron or current, current flow. We can discuss current flow. This transport, how electrons and holes are transporting, depends on the transport, drift and diffusion. They depend on velocity, they depend on mobility, right. The current will flow. And once we discuss about current flow, before that also we have to discuss about carrier recombination and decay. How carriers decay, why they decay, we will talk about that. Carrier recombination and decay, okay. And then we will talk about continuity equation. So, this is the cycle that we will complete in the next perhaps two or three lectures. We have to complete this mobility of carriers, low field transport, high field transport, drift diffusion, current flow, then recombination, carrier decay, continuity equation. Now, after that we are ready to go to p-n junction and devices, okay. So, that is the agenda here. So, we will wrap up the class here today, and in the next class we will again look at, we will start from mobility of carriers, okay. So, we will end the class with the note that we have done high field transport and incomplete ionization today. We are good, we are confident and familiar with carrier statistics, how to calculate electron and hole concentration. Now, we shall start to study mobility and low field transport from the next class, okay. You might have heard the word electron mobility a lot, okay. We will understand what electron mobility actually means, okay. So, we will end the class here. Thank you for your time.